Okay, so I think we're all set to go. Morning, everybody. Welcome to the latest edition of our Virtual Tech Meetup series. It's my great pleasure today to be introducing Sendal Kumar, who's going to be talking today about understanding reactive microservices with JHipster. Before we dive in, just a quick word from our sponsors. So this meetup today is brought to you by LogRocket. I'm sure most of you tuning in today came via our blog. You may not know we actually have a great product for when you're building and fixing applications. So LogRocket is a front-end application monitoring solution that combines error tracking, performance monitoring, infrastructure monitoring, and web analytics. It's all rolled into one solution, so your engineering teams and your product teams can all use a single source of truth to look at every aspect of app development, which allows for more efficient remediation of your problems and iteration of feature sets. In addition, you can also integrate it with all of your existing backend monitoring tools. So for more information, head over to logrocket.com and you can get a personalized demo, or you can just sign up with a free account and get a taste of what our solution can do for you. I would just like to quickly mention that we also have 3 more meetups coming this month. On the 16th of November, the 21st of November and the 28th of November. If any of these are of interest to you, you can head over to the link above, or you can just type in Virtual Tech Meetups LogRocket and it'll take you straight to the page where you can sign up for our upcoming meetups. Now, with all of that out of the way, I'd like to hand over to Sendal to give his talk. For those of you watching, in addition to this meetup we're having now, we'll also be sending a recording to everybody who's signed up, and we'll also be uploading it to our YouTube channel so you can watch this and any previous episode in our meetup series. Now, without further ado, take it away, Sendal.
Oh, thanks, Jack. Thanks. Okay, I don't have a sharing option. Okay, I'm sharing it. Cool. I hope everybody can see the screen. I'm also playing it. Awesome. Let's get started. Hey, everyone. Understanding reactive microservices, the JHipster. That's what we're going to see today. There are 3 main components in the talk: reactive and microservices, and then about JHipster. A little bit about me. I'm Sendal, and I am an engineering manager at Uber, and I'm building payments over here. And yeah, I'm also a core team member of JHipster, and I'm writing Kotlin version of JHipster nowadays, and that's what I'm doing. Agenda, what we're going to see today. We will first start with microservices. What is it all about? And yeah, just a brief introduction because everybody knows about it. And then reactive microservices, why should you think about it? And then how Spring makes it easier for us to build reactive microservices, and how JHipster simplifies the entire process of building and deploying all those things. And finally, we'll try to create a demo e-commerce application and then try to run it on Kubernetes. That's what we're going to see today. So let's start with microservices. So microservices has become a de facto standard across the industry. Every company today has, one way or the other, tried to move into microservices, try to break their monolith and go into microservices and build it. We eventually have 2 companies that have more microservices than the number of engineers inside the company. So we have all sort of funny things there. But the main reason why people are going towards there is basically we have an isolated entities or isolated components or services, and they are completely independent. They are independent to deploy, independent to work with, and you can do all sorts of things in a single small space and then upload it anywhere and you can run it there. So it kind of gives you that environment where like you can isolate everything out and just work on whatever you're going to do, and you're going to do that one thing and do it really well. It also gives the flexibility of granular scalability, like the scaling each and every part of your service based on the amount of resource consumption, based on amount of whatever that it takes. You can scale each of those components as you need it. So that is also one of the biggest benefits of going towards microservices. And finally, the most favorite part for me is fault tolerance. So for example, in your service, if something goes wrong, you can just completely remove that part and still your service as a whole will run with the reduced functionality, but the entire functionality of your service might not have the problem. So you have this fault tolerance available there. So in the world of microservices, since everything is kind of like consolidated into their own isolated space, every service has their own version of data and they can share the state as they want it. So it basically enables us to avoid a single point of failure. For example, if you have one common database for all your services, then it kind of creates a single point of failure. When your database goes away, all your services will have an impact. But if every service has their own data and they kind of like maintains their own state, then it makes it much more easier for you to develop them in isolation. And this is nothing but DDD in a short term, like it's a domain-driven service design, right? So it's all great, right? Like microservices makes it much more easier. All are super nice. You have smaller components that you can work on and then build everything together. But that's not the case because the developer experience is very, very, I would not call it as like terrible, but it has its own impact because you have multiple different services. Now, if you're going to develop something, all these services, if you want to run, set them together and run as an integration test, as a developer, it would be a horrible experience for you to do it because it's going to take consume a lot of resource and everything. So you're going to basically work on based of contracts. That's a bigger problem. The cost of running microservices comparing to monolith on a shorter scale or a smaller scale is much higher than compared with microservices. And monitoring and troubleshooting is also a bigger problem because in the previous world of monoliths, you just have a single entity where you can just see how things are working. And if something is not working, you can debug that single application. Now, in the world of microservices, you have different services. You have to figure out like where it's failing. Finding out that is a huge bottleneck for us. And finally, latency is also one of the biggest concerns. And we will see latency in a much more depth here because that is one of the big problem of microservices. Before microservices in the monolith world, everything is a function call. So if your order team wants to call an invoice, they just call an invoice method inside the function, inside the monolith itself. It's just a function call, and the call can just happen in few milliseconds or nanoseconds even, based on how optimized and what kind of language that you use. That makes it much more simpler, right? But in the world of microservices, you eliminate the network call, function calls, and you put in a network call over there. Now, as we all know, the network is kind of not 100% reliable. It's flaky. And it also takes its time, like there is a latency attached to it whenever you talk about network over here. So whenever you have to communicate, you have to go through the network, and that network will add a latency for your application. That in turn slows your application down. Let's consider the scenario like you have 4 services, and all these 4 services need to communicate with each other. In the world of synchronous way, if a client wants to have a data, it goes and calls the service A, and service A calls the next service here, service B, and it takes a latency of 50 milliseconds. Okay, fine, let's assume that. And then the service A calls the service C, or the third service in the picture, it takes 100 milliseconds. So that is added latency to it. Finally, the service A calls the last service, which is service D, or service the fourth one in the picture, and it adds a 30 plus 20 milliseconds of latency. Now, in the world of synchronous, this kind of adds up. It kind of adds up so that you have the total latency. The customer has to wait around like 170 milliseconds to retrieve the data, because our service synchronously issues orders, collects the data, and then goes back and gives it to customer. So let's assume that like we have 170 milliseconds of latency. But when this scales out to millions or hundreds of microservices, then the number that you're seeing is also going to scale up. From like every service that you're going to add into that picture, you're going to add in latency to your service. And this can grow exponentially in the case of microservices when your services grow. So that is a bigger problem that we have. But all our clients, everybody wants a highly interactive and fast experience. So how can we provide that interactive and fast experience for our clients? And that's where we can use something like async calls here. The service A, instead of like going every service, hopping every service one by one, it can issue a request to all 3 services in an asynchronous way. It just issues a request and waits for them to respond back. And then here, the same example, service A takes 50 milliseconds, and another service takes 100, and then the third service takes 20 milliseconds. Now, the total time for us to respond back to a client is maximum of all the latencies combined, which is in this case is 100 milliseconds because that is a maximum latency. All the other services can have the data. You can collect the data and then form the response and then give it back to the customers much more easily. So in this scenario, if you scale the service, even if you have hundreds of different services that you put in the picture, and all of them have, for example, less than 100 millisecond latency, at the end of the day, your customers are going to wait just 100 milliseconds of time. And we call this as non-blocking async communication, which is a fancy way of saying your application is issuing concurrency or using threads, and then issuing the request and getting the data out of it. That's basically it. So this, how do you change this non-blocking async? Like, what are the benefits of it? It reduces the latency, of course. As you can see in the simple example itself, it reduces 70 milliseconds of latency. And you can have a better latency, lower latency services, higher availability, which in turn. And since it's using threads, non-blocking async calls, which basically enhances or uses the modern architecture that we have, the CPU architectures are built for running in parallel workloads. So it is more efficient for the modern CPUs that we have. So it kind of increases the performance or the resource usage of all the computes that we have. And again, like, it depends on the amount of traffic, and also like for a smaller amount of traffic, this kind of complexity is not required. You can just go ahead with a normal synchronous call, and maybe you can use async calls here and there, but it's not required for low traffic methods. So how can this asynchronous thing can work together? Like in synchronous, you can easily figure out like, okay, it's going to call, I'm going to issue a HTTP request, it's going to give me some data back, and then based on the response, I'm going to call again. But in the world of asynchronous way, the one way of constraining it is using message passing. So all these services can talk about messages, can talk with messages, and can talk to messages. It can be issuing an event, it can be issuing a command, or it can be like giving a response back. So all those things can happen with the help of message passing. And in the world of message passing, there are a few complexities attached to it. One of them is ordering. Your messages has to be in order, right? For example, if you're sending an invoice, before you're sending a payment request, before you creating an invoice and things like that, if the order in which you're issuing messages got messed up, you need someone to wait there and say like, hey, this is wrong, your order is wrong, you should work in order. Like the messages should come in order, or you should wait for the other things to work in order. So that is very, very essential in a message passing system. And then the next problem is consistency. You have to make sure the messages that you're sending are consistent. The messages that you're sending also, like the receiving end of those messages also has to have the capability of handling duplicates. For example, you can send the same message twice, and you should not process the same message twice, and you should have some kind of mechanism which kind of deduces whether it's a duplicate message and things like that, and that's how you can handle them. And finally, if the message is not delivered because one of your services are down and it has to go to different service and things like that, then you have to think about like, how can I optimize those not delivering of messages? How can I retry those things? And those are the major things that you have to think in the world of messaging. And that's where resiliency comes into picture. So in the world of resilient systems, if you're building a system that are resilient, then you're basically ensuring like, I have a retry, I have all those ordering mechanisms, and duplicate messages are handled perfectly and things like that. So that is where resilient systems comes into picture. So in the world of resiliency, I could add in, as I said before, something like retries. That kind of enables us to look for messages, newer messages. Failover, if something is happening, I'm saying like, okay, the order is not correct, I can just close everything out and say like, okay, let's go back from the beginning and reprocess the entire order. And you can have idempotency for duplicate messages and add in like kind of a request UID or a unique identifier for each request, making sure that it is idempotent. And also you can have a deadline. For example, a message you're sending that kind of takes more than 5 seconds or 15 seconds to handle it, and then the response is not there. You can add a deadline and say like, okay, I'm not expecting any more output from that message, I'm just going to cancel it. So in the world of message, if you want to have a resilient system, you need to have this properties like retries, failover, idempotency, and also add a deadline to it. That's where reactive microservices come into picture. In the world of reactive microservices, the reactive part of it is actually based on reactive manifesto. And here, the reactive manifesto says 4 important things. One is responsive. It basically says, anyways, anytime your caller, if they're issuing a request, they should get back a response. And the response it should be as fast as possible, which means you have to reduce the latency and make sure that the users are getting what they're asking. The next thing is resilience, which basically means like the ability to recover quickly. That's what we say, like in the world of message passing and things like that, how we can recover from it. What are the mechanisms like retries, idempotency, and things like that, how we can use that in order to have a resilient system. And then it should have elasticity, which is basically like, even when you scale the amount of processing and things like that, it has to handle in a proper way. That is what is very important in a reactive system. And finally, a message-driven, the system should be message-driven. That is always message goes in and message comes out. And that's how the systems work together. So that is what reactive systems is all about. And that is how you're going to build reactive microservices too, right? So reactive microservices promises on being highly interactive and delivering fast experiences for us. It also enables a consistent and reliable experience. That is where resiliency comes in the picture. It allows your application to scale much more dynamically. So at scale, it kind of allows your servers to work with an optimal resourcing and things like that. And finally, it reduces the resource utilization to a maximum. So since we are using parallel requests, since you're using modern architectures and stuff that kind of like works well on modern architecture, it enables us to reduce the resource utilization. Again, the resource utilization is comparative to the same level of load in a microservices world or in a monolith world. When the load is low, monoliths always perform better. When the load is moderate to high, microservices is good. When the load is extremely high, then reactive microservices reduces the optimization on the resourcing side. So that in turn enables reducing the running cost of your application. If you're running on cloud, it's very essential that you have to make sure your running costs are low. And when you are at the scale of operating like more than 500 to 1,000 requests per second, and you have millions and millions of customers, then I think like going to reactive microservices would reduce the cost dramatically than compared with the normal services. And that is where Spring comes into picture. So Spring enabled us, for Java developers, Spring enabled us to develop web applications in a much more different way. And it kind of like using inversion of control and all those things. And it kind of made it easier for us to develop our applications. Spring's fix is coming up with Java 17 support, which is really exciting. I'm looking forward to it. But Spring brings in all those good benefits and made it easier for us to develop web-based application with Java. And then Spring Boot came in. Spring Boot came in around 2016 or 2015. I'm not too sure on the timeline, but Spring Boot came in. And Spring Boot has dramatically reduced the way in which we write application. And it kind of like, I would like to call it as a cornerstone in the Spring world, because it kind of optimizes everything that we have to deliver, and it delivered the system in a much more different way. It kind of reduced the number of lines of code, configurations that we have to make, and it enabled us to write web application in a much more faster manner. And it came with all the batteries included. Remember the first time when we opened Spring Boot, and then when we run it, it has its Tomcat or Netty instances in it, and it just automatically runs your application. You just have to line 3 or 4 lines of code. And that is really amazing experience. And Spring Boot actually elevated the developer experience that we had. And it also, the Spring Boot 2.0, which came in recently, which came in like around after 3 years of its first release. And it added reactive elements to it. So it enabled us to develop the same Spring Boot application, but made it run on top of reactive system. We will see how Spring reactive system is architected in a later slide, but it allowed us to write reactive applications with Spring Boot. And yeah, I mean, like Spring Boot was very popular, and we always started talking about like, yeah, let's go and make Spring Boot applications better. It had a lot of benefits in terms of like writing it lesser code, and also like configuring dynamically and things like that, which were like very path-breaking during that time. So Spring Boot 2, which is basically had 2 stacks on it. One is the normal serverless stack, which is basically non-reactive application. you can include the project reactor, which is Spring's reactive dependency. So you can include the project reactor and then use the reactive side, which is on the left side. And the runtime is the basic difference here. On the servlet stack, it has Spring MVC runtime, which is the traditional runtime that we had. And on the reactive side, we have the Spring Web Flux. And Spring Web Flux basically is a non-blocking web framework. So this non-blocking web framework is used for reactive. And if you see on the left-hand side, all the components over there are basically reactive. Instead of servlet API in the normal Spring world, we have reactive stream adapters to have the streaming of the application. And then Spring Security, we have Spring Security Reactive too. And also the databases. It also was converted into Spring Data Reactive. So it basically meant like all the parts of the application has been made reactive for the reactive to work together. And that's where Spring Reactive comes into picture. And in the world of Spring Reactive, there are two major concepts. There are like a lot of new things, but two of the most important things that I feel like is mono and flow. Mono is basically, in case of mono, it basically means that it emits 0 or 1 value. Nothing. It emits, considered like an optional thing, where like it emits a value, it has a value, or it just throws an error. That's basically what mono is. On the other hand, flow, basically what it does is like it emits 0 or many values. Sorry. It emits 0 or many values in it. Basically, it's like a list. For example, if you're saying get all places or get all persons, then flow basically gives you a list of values. On the other hand, if you're creating an object, you're just getting one particular object out of it, then you would use mono, which basically is emitting 0 or 1 value. So Spring Boot made it easier for us to write this kind of code. So this is code from a user resource or user controller, where you define the post mapping and say like, this is my endpoint in which you will access this particular function. So here /users, it goes and goes to this function. And here it just, it's a create user function, which creates a user, does nothing. And it has few annotations over here at valid, at request body. The at request body basically mentions like, this is something that will be present on the request of the body of the request, and then it gives the user object to it. And at valid also make sure like it validates that your object structure is equivalent to what we expect. So it kind of does the thing for you. And then you handles over the user to the create user method. And the create user method, first it handles errors. For example, if the main values in the object is empty or something like that, it handles all those errors. And then it calls a repository layer and then goes ahead and saves it. That's basically what it does. And once you get the saved object back, we build a response entity surrounding it. And then we just push in back the body with the updated result. So it made it easier. So this is a single function for creating a user with Spring Boot. If you want to convert this into reactive, then all you have to do is the step-by-step approach where you have a user. Instead of just returning a user, in a reactive world, you return a mono of user. So here we're saying this function might return either 0 users or 1 user. 0 users in the case of error, and 1 user when the save has happened successfully. And then you return that user repository.save, as I mentioned previously. All the components like the data layer, the security layer, and all those layers are reactive, which basically means we can also do it kind of reactive here. So here, instead of just assigning the object and then getting it, doing it in a synchronous way, what you can do is like you can use return user repository.save, save the user, and then does some function on top of it using flag map. And then finally use the lambda expression of the map, and then you return the value out of it. So that's basically it. So it's basically like you're chaining those operations. While in this case, you're just doing the operation one by one. Here, you're chaining all the operations into a single entity. And this is how a Spring reactive-based controller would look like, where you have, instead of using user, you go for mono, and then you chain all your requests down the line. And that's how Spring Reactive works. So if you want to build a reactive Java microservices with Spring Boot and everything, so you have the client, you can have a BFF pattern here, which is a backend for front-end pattern. So you can have one API gateway here. And then after the API gateway, you can have configurations, which is basically the dashboard that you're seeing at the bottom. This is config dashboard. List of services in between, and then you have service registry, which kind of has all the service discovery and all those things with which you can Spring scan. So all these Spring microservices can identify how to connect and where to connect. And then finally, at the end, you can have some data brokers or message brokers and the databases, and everything you can run on top of Spring, and all those things are reactive. There is a reactive version of it. So that's what I said, like all the components in a reactive system should have a reactive in it. The database or the layers that you're going to talk, like all should be reactive, or at least have a reactive wrapper surrounding it. That makes us to reap the benefits of reactive system. What are the benefits? As we saw before, as we have seen before, the resiliency, message passing, and elasticity, and also sorry, I forgot the first one. Okay, but yeah, those are the things that we can get it out of there. But again, like Spring Reactive is not for everyone. So it basically, the general rule of thumb here is like if you have more than 750 requests per second, then Spring Reactive can help you out. But if your services have much lesser than that, then going Spring Reactive is not a proper way of doing it. You could just live with the microservices work. But if you want to go reactive, and if you're having lots and lots of requests that are coming in, then it basically helps you out in reducing cost and also have a better performance. So with that, we can develop Spring Reactive. Spring Reactive helps you to develop applications much faster. Then comes JHipster. So JHipster is an open source application generator. So what it does is like it generates an application based on the inputs that you're giving. And I'd like to call it as a development platform. It not only generates just a backend, but it generates a front end, it generates the databases, connections to databases and all those things. It creates Docker files, Kubernetes files that helps you to create all the configurations that are required and everything related to it. So it kind of adds in all of them together and gives you a bundle so that you can just work on the bundle much more easier. And as I said, it generates all the bells and whistles for your application to run, deploy, and also you can work with it straight away. So that's what JHipster is, and it helps you to generate those applications. So how can you do it? So it's basically like you can install the npm package using npm i-g generator-jhipster, which installs the npm package, create a directory, go into a directory, and run JHipster. And that will generate the application for you. Let's go ahead and do that. So I'm here at this location, and I've just created a folder called demo run, and I have installed JHipster. So JHipster is available here. So all I have to do is run JHipster command. So as soon as I run this command, it asks me a bunch of questions, like whether you want to, what kind of application that you want to create. You can choose between monolith, gateway, and microservices. So I'm just going to, for this demo, I'm just going to use a monolith here. And then it also asks me what is the name of the application that I have. Let's give some name here, demo name. It also asks me whether I have to use Spring Web Flux. Remember, Spring Web Flux is a reactive runtime for running reactive applications. So if you want, you can also add that in your monoliths too. And then some package name for your Java folders. What kind of authentication would you like to use, like JWT, OAuth, or session-based authentication? The databases that you can use along with. So we do support SQL and also NoSQL databases. And you can also choose different databases for production and also development. So here in production, you might use PostgreSQL. And on development, you can just use H2 database just to make sure like it's much more easier for you to handle. You can also add in cache here. So there are multiple different caches that are available. You can also pick a cache and then run those caches. Let's go with the default option here. You can also add in another level of hash using hibernate second level cache. And of course, the obvious question, you can choose between Maven and Gradle. And then you can also use JHipster registry, which is a registry that helps you to monitor, control, and scale your applications in a better way. If you want, you can use it, or you can skip it. Let's skip it. And then it also enables you to add a few other options for your application, like Elasticsearch, WebSockets, using Spring WebSocket, or Kafka, Apache Kafka. And also, like, you can also use Open API generators, API first development. So it kind of enables you to add those configurations and build those files for you. So you can choose any one of them. We also have support for different frameworks. So you can choose between Angular, React, and Vue, or there is also some of the frameworks we support using Blueprints. But let's go with Angular for now. It also generates an admin UI for you, some theming for your application, and all those things. You can also add in multiple languages if you want. And finally, you can also add in more testing. By default, all the unit tests for all the code that you're writing and everything is covered. So it kind of like, you can also add more tests to it. And that's basically it. Once you have given answers for all those questions, it creates all those files for you. And let's see how the code looks like here. So it creates all those files for you. And then, as you can see, it's a normal Spring-based application. There is nothing fancy in here. But it has Spring main, source main, Java files over here, and web app over here, which is an Angular-based application. And we use Webpack for bundling everything. So that's how the application is generated. Go back to the demo. Yeah, so we have seen what JHipster allows you to do, right? If you're saying something that's too many steps, I want just to run and see how the applications are running. We also have start.jhipster.tech, with which you could go to online and just go ahead and create your application. You can configure all those application options that we have seen so far in the UI itself, and then generate the application. If you're authenticated with your GitHub, then you can just create those applications and create all those things that is required, and then get a zip file or put it in your GitHub repository as a new repository. You can do all sort of things. If you don't want to install anything, then start.jhipster.tech would help you to do it all together. So as we have seen, like the generator itself provides many options for you. You can choose whatever that is required, and then you can build your applications together. So let's go back to the demo. And now we are going to develop, we're going to create microservices application. So I'm going to call Thomas demo. Let's see what we have here. So JHipster, in addition to just using the command line interface and also start JHipster.tech, you can also use something like JDL, which is JHipster descriptive language, to create your applications together. So here you're seeing how, you can generate your application using JDL. So you can just say this an application as an application config, and then add in configurations for your application. So I'm having an application here named base name, that's LR store, LogRocket store. And I'm defining the application type as gateway. So since we have mentioned an API gateway kind of an architecture for backend for front and pattern, I'm using gateway. A package name, I've used a service discovery of Eureka here. And I've also used database PostgreSQL, and then the build tool is Gravel. I'm using the client framework React, and I'm mentioning reactive too. That's basically it. So it generates reactive-based application for me. Similarly, I've also have another application, which is my product application, which is simply a microservice. It's not a gateway, as we've seen before, but it also uses Postgres. It uses a Haskell cache, and then it is also reactive. And then I have my third application, which is another microservice. This is an invoice microservice, which is almost similar with Postgres and also with reactive. Finally, I have my fourth microservice, which is a notification microservice. And it uses a MongoDB as its database. It's a different database. And it also is a reactive application. So I have my 4 applications here for my e-commerce suite, which is store, product, invoice, and notification. These are the 4 applications that I have. And then added to that, I also added something called entities here. So entities actually help you to create all the domain object, all the CRUD repository for those entities that you have defined. So here I have an entity, I have a lot of entities here, which is customer with some properties inside or some fields inside here. So I have first name, string, and then the required field, basically the validations that are needed. I have some enums here, genders and enums. So you can see here some enums to configure. And I also have email, which is a string required, and I can also define a pattern, like this should follow this pattern as a validator. So I have all those values here. So I have a lot of things, and also I mentioned a relationship. So a customer is related to user. Basically, we will have a login user. So customer is related to login user. And I can also customize the service that I'm generating. So I'm here saying, hey, I'm creating a service for a customer object. So customer object will have service, customer service. So your customer resource or customer controller connects to customer service and then goes from there. That's how, like, I have a lot of entities. You can see the code over here and a lot of things. Once, like, I'll share the demo with the team. So you have everything. So all I have to do here is basically to go and run JHipster, import the JDL, and then the name of the JDL. And that's basically it. I'm also going to add a skip install for me to skip the install of NPM modules, which makes it much more faster, since it also has web code in it. So as you can see here, it generates 4 folders for me: invoice, notification, store, and product. So if I take a look at store, it's again a normal Spring Boot based application, but this is a reactive application. So if I go to stores, main, Java, and then inside web, REST, I have all my controllers here. And you can also see I have customer resource here, which is basically an entity that we have added, right? And if you go here and see, my customer resource is a normal Spring Boot based or Spring Boot based controller. There's nothing fancy in here. I have customers. See here, it returns a mono rather than it's just returning a response entity of customer. It just returns a mono here. So here, again, the same code, create customer, it returns a mono, and then I do all sort of functionalities, all sort of things, a chain, all sort of things on top of what I require for that customer service. As I said, I needed a customer service, so it calls the customer service over here, and this customer service is connected over here. So customer service takes in as customer repository, so it calls customer repository, and it is the save functionality, and it is calling reactive CRUD repository. So it's basically, instead of calling the normal CRUD repository, it goes and calls it reactive CRUD repository. That's basically what is happening here. And similarly, I have my web app, and my web app also has all the code. It's a standard it's a standard React application since we have used React here. So it has the index with store and everything binded to it. So it basically has all the bells and whistles covered. The another thing that it also generates is Docker files. So you also have all the Docker files. If you want to run this application inside Docker, you can just go ahead and run this application using Docker. So all the bells and whistles are configured for you. So it creates the Docker file, for example, for the image, the options that you want to provide for that particular entity, how you want to run it, what is the port to bind, what happens for your database, what is the username and password, and all those things. So it creates everything for you out of the box. With that said, this is how you can generate a microservice with the JHipster, and the JDL helps you to put all the entities together, build them into an application, and then you can just go ahead and generate the application. Let's go back to the demo. And in addition to that, JHipster also supports blueprints. So in the world of blueprints, again, like blueprints are nothing but like taking particular component out and then putting your own custom component inside. Some examples are Kotlin blueprint, which basically is like, instead of generating the entire backend in Java, it removes the complete Java code and then uses Kotlin code for that. Similarly, you can also use Node.js and .NET. So we have this official generators for them, so you can create all the backend with Kotlin, Node.js, and .NET. And also, we also have, like, instead of Spring, if you want to have like something like Quarkus or Micronaut, we also have support for them. So we generate Quarkus backend instead of Spring backend, and also a Micronaut backend instead of Spring backend. So you can choose between these applications. Again, these are blueprints, which are like pluggable components that we have, and this is developed by our community itself. If you want, you can also generate your own blueprint that could help to deliver applications together. So, all right, that's great, right? If you've got JHipster, you can generate the entire application. We could also try running the application that we have generated. So let's go here. So we have the application that is up and running over here. So let's go to our service. First, let's start with the store. So let's go to the store, and we will first run the store, Gradle run, or just Gradle W2. Additionally, we also need to, since it's a microservice, we also need to run the Docker file. So let me go to source, main, Docker. Let's run the JHipster registry. So Docker compose, JHipster registry. Okay, sorry, this is not Docker compose. Let's wait. Okay, so let's first run the application. So let's see first the application is running. Yeah, so the application is installing all the NPM modules that is required. Let's give it a minute, and it should complete. Yeah, so let's come back to the application, because once it runs, then it makes it easier. So let's go and check about Kubernetes first. So in the world of microservices, we have our applications, everything are running. And once you develop the application, you need to deploy it somewhere. And that's where Kubernetes comes into the picture, because it simplifies a lot of complexities in the microservices world with its own ability to manage your application in a containerized format, right? So all your applications, all your services work on based on contracts. So we have seen how different entities created different REST endpoints, and using that REST endpoints, you're going to work these services communicate with each other using those contracts together. So that's how the contracts work here. But when you scale it in a much higher sense, like when your number of services increases, it will be difficult for you to understand how to connect for a correct service and that service too is running. You cannot do it automatically. You need someone helping there. And how can you scale the services individually? Because that is the main benefit of microservices, granular scalability, and how you can do it. And then how will you know whether a particular service is running at that point or not? The Docker containers, if you're running them in containers, Docker containers, doesn't know anything about it. It just looks whether the process is running or not. If the process is completed, the Docker containers might die. And you will not know whether the service is running or not just using Docker processes. So you need to understand how those things kind of wrap together. And finally, these services are running out in the wild, and you need to know how to safely update some configurations or passwords that are hashed in that file. So that's where Kubernetes comes in, and it helps you to build, deploy, and scale the containerized application in a proper way. And Kubernetes comes with a few different namings in it. So there are a huge ecosystem of different names in it. And let's see the most important things for this demo. One is containers. Containers here represent the Docker container, actual Docker container itself. So in case of our application, if you have a store app, then the image name of the Docker container, which is basically the image that you have in your Docker repository, that is basically what it is. You can define the environment values to it, the same way in which you can define what is your database connection, what is your service registry connection, and all those things. You can define all those environment variables inside there. And then you can also define how much resources each of these containers can take. Like, for example, how much the container can take first, and how much you're going to limit, for example, in memory or the CPU and all those things. And finally, you can also define the port, which is going to be exposed to the external world or outside of the container, through which we can connect to container and get the values out of it. When you have 2 or 3 or more containers together, pack them together, in the Kubernetes world, we call them as pods. Pods are nothing but 1 or more containers. That's basically what pod is. So every pod in Kubernetes has 1 or more containers attached to it. And then we call something called deployment. So deployment usually includes containers, that is pods, a group of pods, and then it also gives some metadata attached to it. As you can see in the YAML file image over there, if you have seen a kind deployment, you added the metadata for it, the name, and then the namespace in which the pod is going to live, the containers are living or running, and then how many replicas you want, any identifiers that you want to use, versioning for that, and then your NTL list of containers. That's how a deployment is defined. So in a Kubernetes world, a deployment is all about list of containers, which is pods, and the metadata to identify them. That's how deployments are defined. And the most important thing to see here is this two last segment, which is Readiness Pro and Liveness Pro. It basically gives you two endpoints, like your application exposes two endpoints. And Kubernetes uses these two endpoints to check whether your application is ready and it is alive. So how it does is like the readiness probe is basically like, it initially waits for like 20 seconds or something. And then for every 15 seconds, it issues a request to the given endpoint. For 6 times, it gives that request and it expects at least once the application to be ready. If not, it will restart the pod itself or the container itself. So that's how Kubernetes works. It continuously monitors whether your application is ready after initial delay seconds for 6 times. And if that fails, then it restarts your application. Once it got a ready message, then the liveness probe kicks in. In the world of liveness probe, it basically like waits for 120 seconds and then hits a different endpoint to check whether the application is alive or not. If this endpoint is going to give an error or like it's not responding for you, then Kubernetes assumes your application is dead. And then it deletes or stops that container from running and then recreates a new container for you. So the readiness and liveness probe is very essential in the Kubernetes world. It kind of adds in all the scaling stuffs that we needed. And then you have the deployments, which is nothing but your application. Now you need a service layer on top of it, which kind of exposes it. And that's where service comes in the picture. So in Kubernetes, you can define a service. And the service, you can say, you can give labels to it and metadata attached, all the metadata to it. You can also define what kind of service it can be. It can be a type, load balancer type, which is basically adds an IP and exposes the IP. It can be an ingress type, or it can be a node type. A node type is basically like it exposes just the port numbers so that you can have some other kind of mechanism in which you can access those services via that ports and things like that. So that's how it works. So let's go back to our questions, right? Like we have some questions like how can we connect to different services, correct services properly? And that's Kubernetes helps us with load balancing and also with service discovery, which enables us to connect to correct services as and when needed. How to scale services? We have already seen things like resourcing and limitations. You can have some rules on top of that resourcing and limitation. If that exceeds this percentage, then go ahead and scale multiple instances of it. And on top of load balancing together, it makes it easier for us to equally divide the loads. How will we know whether a service is running or not? That's where like the liveness and readiness probes helps us, and it automatically monitors using liveness and readiness probe, and then it starts and stops those services as needed. And you can also use something like config management and secret management in Kubernetes, which kind of helps you to update the passwords on the live. So your applications are running, some password has expired, you want to change it, you can use Kubernetes. So Kubernetes secret and config management services to help you to update those on the fly. So let's go to the part 2 of demo. So as you can see here, application is running, but it tries to connect to the discovery client and the discovery client is not there. So let's see what the applications are. So application is running on 8080. So as you can see, I can go in and enter the password. And then it also has all those entities here. But remember, I just started one service here, which is my base service. And the entities that we have, notification, product category, and all those things are from different services. So if I try opening this now, I should get an error. Yes, because the services is not running. So what we can do now is like we can use Kubernetes to put all the services on the cloud and then run from there. So I have my cluster up and running already. So let me close this. And then let me go back one folder. So here, what I can do now is like, I can create a folder called Kubernetes. So I'm creating a folder called K8, and then I'm going inside a folder, and then I'm running JHipster K8s Kubernetes. So here it asks again the same bunch of questions for me for generating my Kubernetes configuration. So first, it's a microservice application for which I need Kubernetes, and it lives on this folder. I've selected all the 4 services for which I have to deploy, and all of them are reactive. And then it asks me whether I want to use something like Prometheus for monitoring, but for now I'm saying no. It also figured out like I have used MongoDB, and then do I need to enable cluster database for this demo? I'm saying no. The JHipster registry, which is a service discovery tool that JHipster uses internally to connect these microservices. Whether I want to use like the password that is required for that, I'm going to go with the default one here. I can also add in the Kubernetes namespace here instead of default. I'm going to use JHipster as a Kubernetes namespace. And it also asks me the Docker repository from which it can fetch the Docker file. So I'm going to say my Docker repository, go and fetch it from there. What are the push for how you can use Docker push here? So there are 2 based on the cloud that you're using, you can have your own version of push. That is Cloud push, or you can also use Docker push and things like that. I have Docker installed, so I'm going to use Docker push. It also asks whether you want to use Istio. We are not using Istio today, but if you want to explore, there is also a blog post that I've written, so you can go ahead and refer that. I'm not using Istio. As I said, on the service part, you can choose between load balancer, node port, and GRIS. I'm using load balancer now because it gives me an IP with which I can access the data. And the stateful services, if you want to create anything, it will ask. And basically what it does is like it creates a Kubernetes configuration file. As I said, 3 important things: deployment, which consists of the metadata and the template, and also like finally the store app. And this is the image where it can fetch it from the Docker repository, all the environment variables attached to it, and then the port numbers, readiness, and liveness probe attached to it. Similarly, you can do it with PostgreSQL. So it basically runs a PostgreSQL. It takes a PostgreSQL image, Postgres 40.5, and then runs it using this stuff. And then it also has this service. Basically, it is a load balancer type, and it is one thing that will be exposed from here. Remember, we just created a backend for front-end pattern, which basically means like store is the only thing that will have user interface. You will not have user interface on these particular things. So there is no need for us to assign a load balancer here because it will not have a user interface. And once I've created it, all I have to do is build the jar, bundle the jar, and also push it to the repository, which is basically this thing here. So I created jar using the prod, and then push it to my Docker image as a Docker image to my repository. Once I've done it, I can run bash kubectl -f, which kind of deploys my entire application on the cloud. For the time's purpose, we are very close to 8 now. So I have already done this before. So I have my application instances up and running. So as you can see here, I have registry, invoice, notification, product, and store with all the databases that is required there. And then on the services, if you take a look at it, it will all be there. And then the store exposed via an external load balancer. So I can click this and my application runs here. So here, let me now using my password. So my application is here. So I can also go to product category here. Now you will not see an error because all the other applications are running over here. So which basically means like you will not see any errors here. And let me go here. This is my local host. Yeah. So I can also go and add here. So it creates all the bells and whistles, as I said, like it creates the add page, edit page, view page, and everything. So everything is created for you. It also has like all those entities. You can also see a gateway here. So this gateway tells you like, hey, look, your application, since I've logged in as an admin, I could see this thing like, hey, your product is running over here, your invoice is running at this location while JHipster registry is running, and there are 2 instances of JHipster registry. So it gives you all the information as an admin you need to know inside here. So that's how the reactive microservices work together. And added to that, if you just want to create, okay, so I've created a reactive microservices, I have my microservices ready, and all I need is microfrontends too. In JHipster world, it's much more easier to do it. So this is one way in which you can generate microfrontends. So I'm gonna close everything out and see like, okay, so this is how you do it. So you just basically, instead of going and adding everything out, you just need this one line where you say microfrontends and put in your service name. So in this example, there is a gateway where you put in microfrontends and put all the service name that you want microfrontends. And that's basically it. So if you can take a look at it, like this is my gateway where I have my web app, which is my front end. And similarly, if I just go to store and see, I will also have a web app here. So that's how microfrontend is architected. So you can configure them together, and it's just adding one line of code. It generates everything and splits them out for you. That's how it works. So let's go back to the slides. Yeah, so let's just see what we have seen. So we have seen microservices, how splitting those huge monoliths into smaller services enable you to scale faster. We have talked about reactive, how we can make things faster and also resilient. Hipster or JHipster, which makes it easier for you to develop and deploy. And finally, Kubernetes, which kind of helps you to manage and maintain your services at scale. And we also seen a demo in which, like, if you were able to generate the application, but I've deployed the application before itself, just to make sure the demo works. And that's basically it. We can also try it now. So for example, we can also do the e-commerce demo, and then we can go to store app, and then go to K8s, and then I can run this -ctl kubectl -f. And you can see here, like, basically I haven't changed any configuration. So it kind of goes ahead and deploys everything together again. Since it's unchanged, there will not be any major change on the Kubernetes front. So you just have to run this command to enable it running. That's basically it. Yeah, so there is also Kotlin JHipster, which is basically like moving all the Java code that we have seen into a Kotlin code. I just released a new version yesterday, which kind of supports Spring 2.7.0. So if you want, give it a try. Feel free to ask any questions. I know, Jack, do we have time for questions, or can we skip over?
Hi, Sandal. Thank you very much for your excellent talk. I think someone's just asking what version of Java is required for this.
Yeah, so we have we support Java 11 plus. So Java 11 is the base version that we have, especially with the new JHipster 7 release. So it also ties back to what version of Spring Boot that we are using. So now we are using Spring Boot 2.7.0. And whatever it supports, we will support. And moving forward, Spring 3, I think it comes with Java 17, if I'm not wrong. So we will also support Java 17 when we move to that.
Okay, awesome. Yeah, I think we're just running out of time as it happens, because we're just about on the hour. But yeah. I just want to thank you, Sandal, for your excellent talk. And just a reminder to everybody that we will be sending out a recording of this, and a recording will be available online as well, to view at your convenience. And just to point anyone who's watching in the direction of our other meetups, which you can find on a URL, which we'll be sharing wherever this video is hosted, and also via our emails. So thank you, Sandal, once again for your excellent presentation. And thank you, everybody, for joining us.
Yeah, thanks, everyone. Thanks for your time.